In this video, I want to give you a brief introduction to HDL. So HDL is the abbreviation for hardware description languages, and it is being used to specify logic functions for the purposes of simulation and also synthesis. Something that you should keep in mind is that HDLs are not being used for synthesizing the circuits. For that purpose, we use computer-aided design or CAD tools that are being used for synthesizing the optimized gate that we have for our functions. So most commercial design are built using HDL. So there are two leading HDL in the world. One is SystemVerilog, which was developed in 1984 by Gateway Design Automation, and it became an IEEE standard in 1995. And there is another one which is called VHDL, and it was developed in 1981 by the Department of Defense, and it became an IEEE standard in 1987. So for this course, I'm gonna focus more on SystemVerilog because it is much more intuitive and easy to understand. But that doesn't discourage you from learning VHDL too, because a lot of the concepts are similar between the two, and many of the commercial software that are being used to develop codes using SystemVerilog or HDL support the other language too. So after building the codes with SystemVerilog or VHDL, we can do simulation. In the simulation stage, we can provide the inputs that we want for our circuit, and then we can check the outputs to make sure that if they are correct or not. And this is a good way for saving the investment, especially since it is going to be more time consuming to build the circuit and then test it rather than do it in a simulation environment. And then finally, for the synthesis step, we can transform the HDL code into a netlist that describes the hardware, and there are specialized software or a specialized CAD tool that are being used for building those circuits. Again, we are not going to go over them. So one thing that is very important for you to consider is that when you are using an HDL, you should be thinking of the hardware that the HDL is producing. So because of that, there are some considerations that might be different than other programming languages. So we will get to them at a later video. So to start with SystemVerilog is built based off of concepts of modules. So a module, you can say it's a black box. We have a certain set of inputs and we have a certain set of outputs. So there are two types of modules in SystemVerilog. We can have behavioral modules, which describe what a module does, and we can have a structural module, which describe how it is built from simpler modules. So let's just take a look at one behavioral module in SystemVerilog. So when you look at this code, there are some things that you probably automatically recognize. So we have input, this is a keyword. We have output, this is another keyword. And we probably can guess, okay, so when it says input, that means that whatever comes after it is probably the input, right? And that's in line with what we saw in the previous graph with the black box, right? So we know A, B, C are inputs, right? Y is output, at least based on the conventions that we had before, that inputs are usually to the left or top of the circuit, and outputs are usually to the right or bottom of the circuit, right? But now when we look at the module itself, you see that it kinda confirms that. So we have input, we have this logic keyword which we didn't got introduced to before, but we have A, B, C, and then we have output which is Y. Another thing that we might notice is that we have module and end module that basically specify where the module begins and where it ends. We can have this, which is called example. We can guess that this is the name of the module that we are creating. And then inside this module, we have this term, which says assign y equal, and then some codes that we don't know what they are, right? So as I said, there are several things to consider. The first thing is module end module. It is a requirement for defining any module in SystemVerilog. So anytime you want to define a module, you should have module and end module at the beginning and end of the module. The next thing is the name of the module that you want to define. So here we named it example. And then inside the example, inside parentheses, we have the list of inputs and outputs. So we can easily see input and output. It makes sense. But what is logic? So logic is being used to specify that these variables are logic numbers, or they are true or false, right? So this also we learn. As for the functionality of the module, we have this assign, which is another keyword in SystemVerilog, and then we have y equals tilde a and tilde b and tilde c, or a and tilde b and tilde c, or a and tilde b and c, right? So now that I read it out loud, you can see what it means, right? Except for the tilde, right? So there are operators that you can use when you define SystemVerilog modules. So tilde is the operator for producing the NOT, or the invert of a logic variable. So if it's 0, it makes it 1. If it's 1, it makes it 0. We have this sign, which is used to define the AND operator, and we have this vertical line, which is designed to define the OR operator. So now based on this, we should be able to easily write down the function y equals a bar, b bar, and c bar, or a, b bar, c bar, or a, b bar, c. So this is the basic functionality that we want to have for our SystemVerilog module. But after defining the module, what it comes is the simulation part. So for the simulation, you can think of it as creating the truth table for this function. So what you basically do for the simulation is that you specify the sets of inputs over a period of time, and then for each one you calculate the output. So for the function that we had, a bar, b bar, c bar, or a, b bar, c bar, or a, b bar, c, if you want to create a truth table, the first row was when a, b, c were all 0, and that's exactly what we have. A is 0 here, b is 0, and c is also 0. So this one, this column is with regard to amount of delay that we can have when we want to do the analysis, right? So for now, I'm just gonna leave it as 0, right? I'm gonna explain it later on. So for that function, y equals a bar, b bar, c bar, or a, b bar, c bar, or a, b bar, c. So you see when a, b, and c are all 0, this term is going to be equal 1. And that's exactly the value for y, because this term is 1, this term is 0, and this one is 0 too. So 1 or 0 is going to be 1. And that's exactly what we have here for y. When a is 0, b is 0, and c is 1, in that case this function is 0. And that's what we have for the output y. When A is 0, B is 1, C is 0, again the output is 0. So we have 0 here. And when A is 0, B is 1, and C is also 1, the output is 0. So we have 0 here. So as you can see, this is basically the same truth table that we had, but now it's kind of sideways, right? But nonetheless, we basically change the inputs over time, and we create all the possible combinations. And then for each one, we basically record what is the output. And after that, after the simulation is done and we verify that the functionality that we want to have is accurate, we can do the synthesis. So this is the result of synthesis of this function. Of course, one thing that you might notice is that here, for the original function, we had three input AND terms or mean terms, and to create the whole function, we had the 3 input OR gate. But now the result of synthesis has two input AND gate and 1 2 input OR gate. The reason for that is in the process of synthesis, we actually can do simplifications too, whether we want it or not, right? So depending if we require simplification or not, we can do that during the process of synthesis, and we get a simplified version of the function. So there are some syntax that you need to follow when writing programs for SystemVerilog. One is that the language is case sensitive. So for example, if you use reset and reset in these two forms, they are meaning different things, right? So this is something that you should always pay attention to, that the name of the variable that you define or the keyword that you want to use, they are case sensitive. The next point is that you cannot have any names for your variable that start with number. So for example, if you want to create a 2-to-1 multiplexer, you cannot just name it 2 mux, right? Because the name cannot start with a number. The next point is that if you have any white spaces in your code, they will be ignored, right? So this is something that you also need to consider. And then finally, if you want to create comments in your code, basically lines of code that are only there for explanation purposes and they don't have any functionality, if it's a single line of code or single line of comment, you can use 2 slashes, and then whatever comes after this 2 slashes in the same line is considered as comment and won't be executed. If you want to have multiple lines of code, you can use a slash, a star, and then star, a slash to basically specify the part in your code that is going to be considered as comments, right? So, and this can be several lines of code. As for the structural modeling, as I said before, structural modeling is basically talking about some functionality that can be broken down into smaller parts. So let's just say we want to implement the same function as before, y equals a bar b bar c bar, or a b bar c bar, or a b bar c. But now we want to do it in a more structural manner. So since we have seen that we have let's say some AND gates, OR gate inverters, right? We can define individual modules for those purposes too. So for example, let's just define a module called AND3 in which it calculates the AND of A, B, and C. So we have again the inputs and outputs, basically the keyword that they specify. Whatever comes after this is the list of inputs, whatever comes after the output is the list of output. And then we say assign y to be the AND of A, B, and C. And then we have end module. So SystemVerilog knows that you started defining a module and then the module now ended. We can have another module for calculating the inverse of a logic variable. So for the inverse, we only have one input and one output, and y equals tilde a. So again, we have module and module. And then let's just define a 3-input NAND gate based on the two modules that we have defined before. So you know, a NAND gate is basically an AND gate followed by an inverter, right? So if you want to define the 3-input NAND gate, you can say you have A, B, and C as the inputs. You have this intermediate or internal signal. So let's say if I want to define the NAND gate by an AND gate followed by an OR gate, you see after the result of AND gate is finalized, you need to assign it to a variable. So this is what we call it here as N1. So we say AND3 is AND gate, A, B, C, and N1. So you see the order of the variables that we put for the function is the same as what we had initially. So we have inputs A, B, C, and the output is Y. So one thing that you need to consider is that these names that we give the modules, right, for the inputs and outputs, they are only defined for that specific module. So it doesn't mean that whatever variable that you want to use as inputs to this module, they should have the same name, right? That's exactly what you see here. So we have A, B, C, but the output is called N1, right? So that means the same thing can be applied to A, B, C too, right? So you can have whatever name for these variables and it still would function. And then we have in the inverter function with input N1 and the output being Y. So one thing that you notice here is that we have this AND3 and INV modules, but now we have these additional names too, right? So the way that SystemVerilog works is that when you want to call a module, you basically create an instance of that module, right? And then you name it again. So this one is called AND gate, and it is an instance of AND3. This one is named inverter, and it is an instance of the INV module that we had before. Of course, in the later videos, we will go into much more detail about these requirements and functionalities of SystemVerilog.